Hello and welcome to a coding challenge, a calm, soothing, although somewhat turbulent coding challenge called fluid simulation. Now I have something to admit to you. I don't really understand how any of this stuff works. I did make this at one point, and so I'm hoping in this coding challenge to recreate exactly this, which will be a basis on which hopefully a lot of other interesting ideas will come about. This idea came into mind when I recently saw Smarter Everyday's video on laminar flow. You know, I love laminar flow and all, but team turbulence for life. Mwah! All right, so there's a wonderful 3 blue 1 brown. Do I just reference the same other YouTube channels every single time? Yes, I do. But there's also an excellent 3 blue 1 brown video on turbulence, which I would also recommend. So let me give you some background here. So first of all, there is a GitHub issue thread which started by deardanielxd from 2016, Latzman-Boltzmann methods for fluid simulation. So this is one method, but what I want to highlight here is that what I want to highlight here are these 3 links. So the seminal kind of canonical standard, or the origins of doing like fluid dynamics in computer graphics in my research comes from this article by Joss Stam, Real-Time Fluid Dynamics for Games. I believe this is a SIGGRAPH paper, 2003. Somebody fact check me on that. And it's built on top of this idea of these Navier-Stokes equations, which are these partial differential equations that describe fluid dynamics. And there's actually a $1 million challenge for proving that this can or cannot be solved in 3 dimensions. None of this is anything I'm capable of doing. But this paper includes some of the formulas, includes a lot of the code, and you can see one thing that's sort of key concept here is a fluid simulation can be done by thinking about fluid as kind of particles that live in a grid. Obviously it might be like an infinitely small grid in real life, but we can make that discrete and think about the grid of pixels and what the sort of density or the velocity of each of the fluid is at every one of these spots on the grid. That's ultimately what I'm going to do. And there's some nice C code and descriptions of some of these algorithms. So this article, I believe, serves as the basis for Memo Atkins' processing library called MSA Fluid. This is also an open frameworks library, which is a C++ engine. And you can see here the way that this ends up looking by sort of like distorting this vector field. Oh, this is awesome. Oh, I'm sure the YouTube compression is totally ruining this, but it's beautiful. Check out that library. You should also check out Gabriel Weymouth's, I hope I pronounced that correctly, LilyPad project, which was actually, I believe, used in the 3 blue 1 brown video on turbulence. Gabriel writes here at the end a bunch of things about Stam's approach and what LilyPad does, and a paper. So this is a giant rabbit hole you could go down. And I have spent some time sort of like poking around in this rabbit hole in the last week. The article that I found that I kind of enjoyed the most in terms of style was Mike Ash's article called Fluid Simulation for Dummies, which is actually a but a version of Joss Stam's paper, but actually turning it into 3D and how to render that 3D with parallelizing computing power is all here in his master's thesis. That's another rabbit hole you could go down. So what I would like to do is use this article, and I try to make sure that I don't repurpose somebody else's content without permission, even if it's sort of on the web in an open source way. What I want to do, I asked Mike Ash for permission on Twitter, I think it's @MikeAsh, but I'll include a link in this video's description, if I could go through this in a video. And so what I'm going to do is I'm going to go through this in the video and mostly just kind of like copy paste this code, which is written, I believe, C++ or C, something like that, some object-oriented C flavor language. And I'm going to copy paste it into processing, which is a Java-based programming environment, and kind of like adjust the code to work in the way that I know and see if I can get the result and play with the result. So I don't feel obligated to understand or explain all of the maths involved throughout all this, and I would definitely encourage you to read this, or I would probably stop and read this whole article before you continue watching this. And then this is going to be in 3 parts at a minimum. So this first part, I hope you just like get it working. I just want to copy paste the code, change the syntax around, get it rendering, and play with it. Number 2 is I want to kind of refactor the code. That's will be in another video. I'm actually going to refactor it in with a kind of modern approach. Maybe modern is the wrong word. I mean, this was done in like over 10 years ago, but I want to use like object-oriented programming, vector, like the Pvector class in processing. I think there's some ways that I can redo the code to make it a little bit more readable than this particular style that uses a lot of like esoteric variable naming. So that's number 2. And then number 3, I want to then apply this logic to my my flow field example from the Nature of Code book. So if I could take the fluid simulation, turn it into a vector field where I could just toss particles in that fly around, I think some visual opportunities will come of that. So that's 3 parts. Just get the thing working. That's what I'm about to attempt to do right now. I'm sure it will go wrong, but I will try my best. Number 2, refactor the code to make it sort of fit with how I think about coding and processing in P5GS today. And then also try to do some more stuff with it visually. And I would say one of the things is there's going to be some performance issues. I'm going to keep things low resolution, but you'll see a lot of the implementations of this use shaders or WebGL and all sorts of fancy tricks that I'm not going to get into, but if you know about that stuff and can build on top of whatever I'm doing, then fantastic. All right, so I'm about to get started coding, but before I do that, I've written in advance like a bunch of the concepts that are involved in this implementation that I want to make sure that I don't forget to mention. The first one that I think is really important is this idea of an incompressible fluid. An incompressible fluid is a fluid that's density must remain constant throughout, like water. So for example, if you have water in a balloon and you squeeze that balloon, the water's got to like come out. It's not compressible, whereas air is actually compressible. Its density can change. So this apparently, from the little research that I've done, simplifies a lot of the stuff. So this fluid simulation is going to work only for this idea of an incompressible fluid. I should also mention that the goal here is not necessarily to, with scientific accuracy, simulate like true fluid mechanics, but rather to create the illusion and feeling of that through like some like remote connection to that actual scientific accuracy. But I'm sure whatever I do will be less accurate than what people have done before me based on how I know the way I make things. All right, but that's an important thing. So the first thing that we need to consider is that the fluid is going to live inside of a box. And the way the math is sort of tuned in these examples, I believe, is so that this box should really be a square. And sometimes, like I don't know why, like a power of 2 is always a nice thing. So maybe I'll start with like 512 by 512, or maybe 256 by 256, just to make it low resolution. So you can think of this as a grid of pixels. And there is going to be inside of this grid a velocity vector. A velocity vector that points in a given direction. So if the velocity vector in every spot in the grid is 0, it's like completely still water. If I put a velocity vector moving to the right, it's like the water that would be like laminar flow, by the way, I think, because the velocity of everything is smooth and perfect and all moving in exactly the same direction, as opposed to turbulence where everything's kind of going crazy. So that's one thing that's going to exist in here. So that is something I should say. There is this idea of the velocity field, or the vector field, and that's going to have x's and y's. In Mike Ash's blog post, it's actually all done in 3D with x, y's, and z's, and I'm going to take out that third dimension while I'm doing it. Then, but you should add it back in and see what happens there. Now, the other thing is there's going to be this idea of die. Oh, I wrote this over here already because I wanted to explain that. There's this idea of die. And we're going to talk about the density of the die, which is, in other words, this vector field, we wouldn't be able to see anything moving through. We wouldn't be able to undersee the flow through the fluid without like putting something in it. So you could imagine sprinkling a little dye in it and having it diffuse, maybe Advect, diffuse, Advect, project all around the fluid. So, but what I want to make clear is when we start talking about density in this code example, and this Mike Ash makes very specific it makes a very specific point about. We're talking about the density of this die, which is like an extra thing we're adding just so we can visualize it. We're also able to visualize it just as a vector field, which I will do at some point, but the die is what's going to give it more this like smoky like quality by visualizing the amount of dye that's sort of as it moves throughout the fluid. So this is the basic idea. So the first thing I need to do is get an array to store all of the x's and y's of the vector field and the amount of dye for every single one of these spots. And in the example, it's done with like 3 separate arrays: an array of x's, an array of y's, and an array of densities. And it kind of works like a cellular automata simulation where I need the previous state and the next state, all the velocity of the previous and the next velocity, all the density and the next density. So I'm actually going to need 2. So this is why the code gets really confusing, because I need x, y, and density. Then I need what's in the code named as x0, y0, and density 0. I forget, this might be called like S or something in the code, but I need the sort of previous of all these. So there's a whole bunch of arrays. And this is what I want to later refactor and see if I can just use Pvector or an object that stores a Pvector and a density value and a previous, all that stuff. All right, let's go back to Mike Ash's page. And I'm going to start with this. This is what I was talking about. So this C++ structure, I'm going to take it into processing. I'm going to add setup. I'm going to add draw. I'm going to say size 250. Actually, you know what I'm going to do? I'm going to create a variable called n. This will appear in the code, which is kind of like the width and height of the square. So it will be 5. So n is going to be, in this case, what did I say, 256. And then actually in processing, if you use a variable for the dimensions that you want to put in size, you've actually got to put that in the settings function. So I can say this. So this should get me like a 256 by 256 window. And then, so I'm going to save that. And I'm going to call this like fluid sim ash and stam, fluid sim ash stam. And then I'm going to create a class. And I'm going to call this, make a new tab, I'm going to say class fluid. And in that class, I want to have all this stuff. All of these. Now, the thing that's different here in processing is this star. What is that star? What does that star mean? And that's actually because it's some C-flavored language in the code in Mike Stam's. That is a pointer, meaning it's pointing to an area, a memory address of the computer where all the density values will be stored. But what I really want this to be is just an array. So I'm going to change all of these to an array, which is the same thing in Java. This is now a pointer to an array. You'll see in a second. And then, and by the way, I'm going to take out all the z's. I should mention, so these variables, this is a diffusion amount, like which is like a variable to control how the velocity and sort of the vectors and the dye diffuses throughout the fluid. This is viscosity. Viscosity is like the thickness of the fluid, so playing with that can change the behavior as well. dt is the time step. In all of my physics simulations I've always done, I just have the time step of 1, but I think you need a smaller time step to be able to get the simulation to behave somewhat accurately. So that'll come up later. And now I have density, and I think this is previous density, velocity x, velocity y, previous velocity x, and previous velocity y. All right, so now this is creating it. So I basically want to do exactly this. So this would be in the constructor of the fluid. And I'm not making it, and basically, n I already declared somewhere else. And I think so. I don't think I need size. I'm going to say cube size. And these should all be this dot. So this is referring to the actual variables in the object itself. And I don't need z. And I don't need z. And now, this is like, C-alloc is like a memory allocation, because you're allocating a certain amount of memory for all these fluid values. But I just want an array that has size n times n. So this is going to be this. And it's n times n times n because his is in 3 dimensions. So I know I could do like a find and replace, but this is like so crazy that I want to do this. This is like very meditative for me. Okay, and this receives dt 3 arguments when you create the fluid. You create it with a time step, a diffusion, and a viscosity. So in here I'd be saying something like fluid, and in setup I would now say fluid equals a new fluid, maybe like a time step of 0.1, and I'm just going to make a density and viscosity of 0 for right now, but those values would get filled in presumably. Okay, we're getting there, we're moving through the article. Here we go. This is describing, okay, you need to be able to destroy the thing, free all the memory. Java, garbage collection. I don't have to worry about that. It will get cleaned up for me. addDensity. Okay, this makes sense. Now remember, addDensity is not referring to the fluid itself. It's referring to the dye that's going into the fluid. So this is basically like an addDye. I sort of feel like I want to rename that function to addDye, but I'm going to just call it addDensity. So we're going to take this function. I think this could be a function that's part of the object. What does it need? We don't need a reference to the object itself. We have that. We need a location and an amount. That makes sense. So we need a location and an amount. So that's like the amount of dye we're adding at this XY spot. Now, here's the thing. You'll notice something. Everywhere in the code, there's this like ix function, index equals ix. Well, this is a two-dimensional, this is two-dimensional, but you notice all the arrays I made were one-dimensional. And this is kind of a pretty typical thing to do. So, but I need a way of going from x, comma y to the single index that's a lookup into this grid. So I could write a function, I think it's done with like a macro or a define or whatever in this, but I'm going to write a function, I'm going to name it, I'm going to call it ix. And it gets an x and a y, and it would just return x plus y times n. So this is, it needs to return an integer. It's not void. So this basically says for any given x, y, give me the one-dimensional index. And this formula is the same thing that I use in all my image processing and pixel processing. It's a way to get a 2D location in a one-dimensional array. Okay, so now I would be saying, and we can go back to this code basically, and we can do this, but no z. And then we're basically going to say, hey, this dot, what is it called? Vx. Oh wait, no, that's velocity. Sorry. This dot density at index add some amount. So this is really simple. This is like a really simple function. Just add some density to this spot, this amount of density to this spot. Then we can also do this add velocity, which is basically the same thing, but just with an amount x and an amount y. So I think we could probably just copy this. And we could say add velocity at xy with an amount x and an amount y. See, I would prefer to use like Pvectors for all this stuff. But, and then we get the index, and we say vx plus amount x, and vy. By the way, this is going to get, porting some of this code is going to get a lot worse soon enough. Okay, now, all right. Look at this. So here, now we can take a moment. Here are the 3 main operations. Diffuse, project, advect. Let's do them one at a time. So we can read this. I mean, it's useful to read Mike Ash's description. Put a drop of soy sauce. Soy sauce gives a way of thinking about dye. And you'll notice that it doesn't stay still, but it spreads out. So this happens even if the water and the sauce are perfectly still. It's called diffusion. And so the dye obviously diffuses. That makes sense. But the velocity also diffuses. If some of it moves, it's causing everything around it to move as well. So that's a function. This is really going to be the function that does the solving of the Navier-Stokes equation. So let's do diffuse. So I'm going to put diffuse, and this is not going to be an object inside the class, and I'll explain why in a second. So the first thing that I'm going to do is I'm just going to try to port this. So anytime there is the pointer, I want this to be an array. Diff is a diffusion amount, dt, the number of iterations, n. I don't think I need n as an argument because I'm just using that as a global variable. I also kind of personally would like to just keep iterations as a global variable. I think that'll make things a little bit simpler. Where did I put that? I'm actually going to put these in the fluid tab. That's mostly where I'm working. Final iteration, int iterations. Like we can just put that as 1, but let's leave that as like 10 right now. So the idea here is that this function knows how to diffuse any arbitrary array of numbers, x, based on its previous values, x0, based on a diffusion amount and a time step. But you'll notice that what it does is immediately calls another function called linear solve. So solving a linear equation is like something like this. I don't know. 2x plus y minus 3z equals 10. Right? This is a linear equation. We could have multiple linear equations. And algorithms for solving the sort of set of solutions to this equation, what are all the x and y's and z's that make this true, is known as a process of linear solution. There are different techniques, and I was reading the comments in Mike Ash's paper. There's like this Gauss-Seidel technique. Some people did his code using this. I forget which technique his code is particularly using, but it's a way of basically solving those linear equations for fluid dynamics in the space of this grid. So that's kind of all I want to say about it. But it's needed for every single, for this diffusion algorithm. And it's really just a thing that like passes all the values all around over and over and over again with lots of iterations to sort of spread out and like a cellular automata to have the velocities or densities of neighbors affect the other neighbors and so on and so forth. So I'm now going to go and just grab the linear solve code from here. I'm going to grab this, and you can sort of see what it's doing. So I'm going to grab this function. I'm going to bring it in here. And by the way, this is kind of how I work. Like I kind of want to understand this more, but I feel like I need to just like port the code and play around with it, and then maybe I can do some more research about what the equations actually are and how it's working. But sometimes this like kind of messing with the code, getting your hands on the code can sometimes help you understand the math later. So I'm going to look at this. I'm going to take out static. I'm going to move this bracket over here. I don't need iterations in n. Those are going to be the same for everything. These should be arrays. And the kind of goofy thing here is I don't need m. So I need I and j for x and y, but I can take out m. And so that loses a bracket there. And then I have to look at what's going on here. So I don't need m. And then I also don't need to add these two components. So let's see. So the idea here is that I'm looking at, and this I've done this before. I'm having like a crazy deja vu. What this is now doing is saying the new value of a particular cell is based on a function of itself and all of its neighbors. And you can see that here. It is equal to its old value plus some combination of its current values. All right, so now we're going back to the paper, and we're going to look at the next function, project. Okay, so this project function is really tied to the idea of this incompressible fluid. The amount of fluid in each box has to stay constant. So the amount of fluid going in has to be exactly equal to the amount of fluid going out. So this is kind of like a cleanup stage to like put the set thing back into equilibrium. So we're going to be doing this for all the different values, all the different velocity arrays. So let's grab this. Oh, look at this craziness. So let's grab the project function. Paste in project. These are arrays. I don't need the z. These are also arrays. And I don't need the iterations and n. Those are constants. And then now I also don't need k. I only need I and j because I'm just doing 2 dimensions. I don't need k. I don't need these two. And then I don't have set boundaries yet. I'll add that. Linear solve is the same thing, but without this. And I think I can, when I do set bounds, I'll probably take out the n. Then I don't need k. I don't need k. I don't need k. I don't need k. I don't need z. And I don't need k. I don't need k. I guess probably porting just stance, which was 2D, might have made more sense. And I plus 1j, I minus 1j, j plus 1, j minus 1. Yes, yes, this all makes sense. And then I don't need the z here. I think I lost a curly bracket, which would go here. And definitely screwed up something curly bracket wise. I think I have an extra curly bracket here. Okay, this looks right. Oh, I don't need the k's up here. Missing left curly bracket, and I have an extra curly bracket here. All right, we're good. We don't know what set bounds is, but that's okay. All right, whew. We now, don't worry, we're getting close. So now, advection. The advect step is responsible for actually moving things around. To that end, it looks at each cell in turn. In that cell, it grabs the velocity, follows that velocity back in time. Whoa! So let's grab this advect function, and I could kind of scroll back up. Let's look at what was expanded. Yeah. So this is also important. Every cell has a set of velocities, and these velocities make things move. This is called advection. As with diffusion, advection applies both to the dye and to the velocities itself. So what's really the difference between diffusion and advection? Well, diffusion is just this idea of spreading out. But advection is actually the motion associated with the velocities. They're obviously related, and they both happen together, but those are separate things. So let's go grab the advection code. What? Seriously? Okay. Wow. So this I'm really going to want to unpack when I refactor this to understand what's going on. Well, I'm going to just grab it right now. Oh, this is crazy. I'm going to bring it in here. Oh, boy. Ooh. Okay, ready, everybody? Deep breath. Deep breath. This is an array. This is the current density. This is the previous density. This is the current velocity. Oh. This is the current velocity. I don't need z. Come on, scroll over. So what? What could you, are you kidding me? So these are index and previous index values. We don't need the z. We need a dt for x and a dt for y. We don't need the z. We need, this has to do with like, I think the s's are density in this. I'm not really sure when we look through the code, but I'm going to take out the u. I don't need the 3, and I don't need the z. Oh my God, I don't need the k. I don't need the k. So, all right, so I don't need the k part of the loop, and I don't need this last thing, and I don't need this z. And I need the x and the i's, the y's and the j's, and I don't need the z's and the k's. And I need the s's and the t's. I don't need the u's. Oh, this is really, and I don't need the k's. And now I don't need the k. And so what did I get rid of up here? I'm using, this is what I mean. Like, I really want to refactor this and try to understand what each of these variables are doing and rename them. This isn't refactoring. This is just getting it to work. So I've got i's and j's, x's and y's, i's and j's, s's and t's, and no k's. Oh, wait a second. STU. U was the thing, if I go back to Mike Ash, U was the third dimension for the s and the t's. Okay. So what I'm actually getting rid of is this multiplication step. So one less multiplication step. I think I don't need this at all. This is what I'm doing, yeah. This is much simpler. Oh, you silly third dimension. I'm pretty sure this is right. What's the chance of that? I'm going to definitely have to double check this. Double check this. And then one last thing here. Do I have the right? Okay, floor F. It's just floor, right? Because those are integers. This seems to be some extra flooring that's unnecessary here, because these are floats, but I'm not sure. I'm going to leave it as is, right? And these would then have to be converted. I think there's some extra unnecessary steps here in how the numbers are being manipulated, but I'm going to just leave everything in, and I will, in part 2, we're going to get this to work. Just fast forward like 5 or 10 minutes towards the end. Okay. All right. I'm pretty sure this is now the Advect function. I think I actually have everything but this set boundary. So this set boundary is actually something like really nice and like compared to all that much more manageable to understand. But basically, we've got this kind of unrealistic situation here. Well, it's not unrealistic, but we're containing the fluid within a box. And so we need some sort of mechanism for what we do with the edge cells and how we deal with those velocity vectors or things moving. And basically, we want to add some kind of like bouncing. And then we also need to deal with the corner cells even differently, in a different way. So we can read, this is short for set bounds, and it's a way to keep your fluid from leaking out of your box. Not that it could really leak, writes Mike Ash. It's just a simulation in memory. But if there's no walls, right? It's obviously fluid's not going to leak out of your computer screen. That's what that was, a joke there, and I just like, my mind hurt so much I couldn't even laugh, haha. But the velocity it needs to become mirrored when it hits the wall. So if we look at what the set, and the reason why this is done in this like really weird way is the set bounds function is written in a way that this b variable tells you like which wall am I at? Am I at the right wall, the left wall, the top wall, the bottom wall? And I think that I could rewrite this with vectors in a way that it just kind of like knows. And I don't need this like extra variable b that's passed through. But once again, I am going to port it. So exactly as written. X is any one of these arrays. So we need to we need to do the same thing for all of the arrays, whether it's velocity x, velocity y, or density, the density of the die. And once again, I can actually eliminate, this is for the third dimension, so I can completely take this out. Then I'm going to take out k. And you can see like this is saying if b equals 2, you're dealing with the x stuff. Actually, it's the y, because you can see it's looking at the top row and the bottom row. Sorry. So this is good. And then this is if b is 1. I think I might have messed this up. All right, strange edit point, but I'm jumping in here from the future in the middle of this video to explain something about this set bound function that I kind of botched while I was actually doing the challenge, and I'm at the end now, but I'm going to fix it. One thing that's really important is for me to point out what is written in the article by Mike Ash. Every velocity in the layer next to the outer layer is mirrored. So when you have some velocity going towards the wall in the spot next to the wall gets a velocity that perfectly counters it. That's keeping it a closed box. So that is the explanation for why here I'm saying, hey, if I'm at I, 0, any given x all along the top row, right? If y is 0, all the x's along the top, counteract the velocity from one row down. But only if I've sent in this b equals 2, which is that weird thing. And this I think would be easier with Pvector because I could do this all at once. But the thing that I have in here, I have this like leftover extra because in 3D there's more neighbors. So I actually could take this out. And this is going to make this now look correct. So this set boundary function is actually much simpler. It is just reversing the velocities in all the edge layers according to edge columns. Edge columns are rows according to the next to the edge column or row. And then for the corners, it actually just does an average of the two neighbors. And that keeps it this like walled box. So that's not, in the end, like it's kind of going to perform the same way. I just had this like extra loops in there. But this is like an important clarification. So now continue with the challenge wherever I left off. but this will be the code that's actually there when you look at this later, if you can make it to the end of this video. See you soon. I think we have set bounds now. All right, Oh, all right, fine. I don't think I need to pass in n. N is just a constant everywhere. So let's simplify that. So let's go through this. Fluid is fine. Add velocity diffusion, linear solve. This has to come back without the n. Project, linear solve, boundaries, no n, no n. So a couple things. People in the chat are mentioning, I have no idea what's going on. I kind of don't either. Maybe this isn't a video that's worth watching. I'm not sure. I mean, at this point, this is just something that I'm invested in trying to do, and I will come back to it. But this, I think, is an example of why refactoring and sort of thinking about code and variable naming is a good thing. And there's nothing wrong with what was done before. This is probably perfectly appropriate and quite common styles from like over 10 years ago. But I think we could hopefully do better, and I can come back and refactor this. But I realized that I've totally got this wrong, and I have some code that I did the other day here. There we go. This is what I've been trying to do. I want to add those two things together times S0, and those two things together times S1. Okay. All right, no errors. No errors, no errors. This is, by the way, what I really like to avoid doing. I don't like to code forever and ever and ever without testing. So if this like actually works when I start to render it, I will be completely and totally gobsmacked. Okay, so now I need a time step function. So I need a function, time step, to step through every moment of time with the fluid. Going back to Mike Ash's paper, there is a step function, which I'm going to grab. Of course, I just wrote it out here. But what I want is void step. And I have all these as variables, but let's change that to this dot. Replace float space star. I know you can't see this. Replace float space star with float bracket star. No, float bracket space. I don't need, and I don't need the n or the number of iterations. I don't need the z. So iterations is 4. Okay, so let's look at that. The process here is what? Diffuse the velocities, right? Diffuse the velocities based on the time step and viscosity, the x's and the y's. The 1 and the 2 is controlling the set bounds function. Then project, which is clean everything up to make sure it's the same amount of fluid everywhere, the velocities. Then run advection, advect on the velocities, x and y. Then clean all that up. Then diffuse the density and advect the density. The density doesn't need the project step because the density doesn't remain consistent around. It's the die that actually is moving around and is inconsistent. So we should really be in, we've really got this whole thing programmed now. I should just started with, it definitely should have started with Memo's library. So if I say background 0, and I say fluid step, let's run this. Hey, no errors. Oh, happy day. I mean, give me a, I'm going to be shocked if I can actually render this, but let's actually render this. So first, let's do a thing where as I drag the mouse, I'm going to add die. So I'm going to add die at mouse x, mouse y, some amount of die. Okay? Oh, and I need to say fluid.addDensity. All right, no errors. That's good. That function's called. Now let's try to render. Let's call render d for rendering the density. So how am I going to do that? Oh, you know what I should actually really do? I'm going to change this to 64. And then I'm going to create a variable called scale and make that 4. And then I'm going to say size is n times scale, n times scale. So I'm actually going to like lower it, and let's actually let's make the scale 10. So now we should have, well, if I comment this out, I should have 640 by 640 window. Okay. So now fluid render d I'm going to go here and I'm going to add a function in the fluid class. I kind of want to take all these functions out and put them in a separate tab. I'm going to call this more fluid. So just like the fluid class is here, which has less stuff in it. And I'm going to say render D. So this should be pretty easy in that I'm just going to say int I equals 0, I is less than n, I plus. So I'm going to loop through j, then I'm going to use j. Then x is going to be I times scale. Y is j times scale. I'm going to draw a rectangle at x, y, scale, which is really a square, scale, scale. By the way, did you know that processing now has the function square in it? I'm going to draw a square, get rid of that. That's going to work. I've never used this before. This is a momentous occasion 4 hours into this video. Then I'm going to say fill 255, 100. I just want to see, like, I'm just going to put an arbitrary fill. Great. So I can see all of those squares are there. I'm going to say no stroke. And then now what I want to do is the density is this dot density at the index I and j. And I'm going to make that the alpha. So d is d. So the alpha of that square, I mean, it could just be the brightness, but let's just make it the brightness directly. So it's black. Oh, array out of bounds exception. Okay, interesting. Ah, I forgot. So if I am adding fluid at mouse x and mouse y, I have to divide that now by scale because I scaled up the screen. So that has to be divided by scale. There we go. Okay, so you can see I'm adding the fluid. Great. All right, so that's something. Now there's, I guess the water is completely still. Didn't I say it would diffuse anyway? Let's try adding some, let's try also adding some velocity. So I need to just also add, you know what I'm going to do? I have an idea. When I do that, I'm also going to add velocity at that spot. And add velocity expects what? Expects the x and y and the amount x and y. Okay. So the x and y, and now I'm going to do this. Let amount x equal mouse x minus p mouse x. P mouse x is the previous mouse possession, so the velocity is going to kind of be in the direction that I'm dragging. Not let, float. I'm in Java, not JavaScript. And an amount y is mouse y, p mouse x. So let's add that amount. Y. Let's see what happens here. Oh, okay. I don't mind that so much. We got an array out of bounds exception. So what went out of bounds? All right, well, one thing I can do here. Where's my index function? X equals constrain x to 0, n minus 1. Let's just put a constraint in here. I don't know whether I have a bug in my code or this is actually necessary. But let's do that. Ah, there we go. Oh my God. Ah. I think what I want to do is add something that always like, yeah, because look at this. I'm going to always like fade out. I'm going to add something to like fade. I'm going to add a function called fade d. I should really render the velocity where I'm going to say for int I equals 0, I is less than this dot density. Not length I plus plus. Density index I minus equal 1. And then density index I equals constrain. Density index I. Actually, no. I can just do this. Equals constrain. Here. Float D equals density index I. And then constrain D. I want to set equal D minus 1, but stay within 0 and 255. And then let me add fluid render fade D. I also want to render the velocity field. So just because if I add a lot, I mean, that's too much fade. I just want it to like lose. I just want it to like the die to like peter out. Right now, I think the die is kind of like infinite. I mean, it just keeps, it's additive. So, but this obviously, maybe I just want it to peter out more slowly. All right, so this is a nice little swirl effect. Now, here's what I want to do. I would like to, I mean, the other thing I could do is make this 128 and change the scale to 5. Can it? Yeah. So that's nicer. It can still perform. The frame rate is still fine. So what I want to do is I actually want to now, I'm going to just use perlin noise really quickly. I'm just going to add density to the middle. This is what I should be doing. So what happens if I just continuously add density all the time in draw, and this has to be converted into an integer. This is kind of silly what I'm doing, but it's fine. All right, so now the die is just sitting there in the middle, but I can kind of drag around. But what I want to do now is I'm going to take this, and I'm going to use perlin noise. I'm going to say noise of some time, map noise of some time which goes between 0 and 1 to between -1 and 1. And amount y is the same, but I'm going to look at like a different part of the noise space. If you're not familiar with perlin noise, I would encourage you to check out my perlin noise videos. And then I'm going to say this also is going to be the same at this spot here. So I'm going to say int center x equals this. Int center y equals that. Then add some density at center x, center y. We could actually make this like a random amount of density, maybe. And then add the velocity according to perlin noise. I am going to create a variable called t, which is kind of like the offset through the noise space. And I'm going to have t. Oh, I should be using, I changed my mind. I'm going to use Pvector. And I'm going to say angle equals noise of t times 2 pi. And then I'm going to say a Pvector is a new Pvector from angle. I'm going to create a vector from angle, that angle. And then the time will go up. And this is v.x, v.y. And let's try, I don't know what it should be, but let's try like making the vector a little bit stronger right now. So let's see here. There we go. Yeah, this is what I was trying to do. Maybe it is too strong. Yeah, this is kind of the idea. I'm not seeing, I just wanted it to kind of like shoot it out randomly. Let's take out the fade. Let me try, someone tell me I swapped Vx and Vy at line 96 and 97. Okay, thank you. So that's an important fix. I mean, visually we were getting some result anyway. Let me go back to making it, let me do this. Let me add. All right, one thing I could try, I think you get the idea. But one thing that I could try is I could try kind of adding some density in like all in a little grid pattern. So this might be sort of nice to do. And then I could say plus I. So this is just adding a lot more density. And let me turn that back to 0. And yeah, that's kind of, this is more like what I wanted. There we go. Okay, that was the velocity was too strong. Okay, so here we go. This is more what I was looking to try to do. I've got sort of perlin noise controlling this angle. I'm just like dropping in dye constantly. It'd be sort of interesting to like sprinkle dye everywhere. There's so much you could do with color to drop particles in. So let's recap what I've done. I wanted to have some type of visualization of turbulent fluid. I think I mostly have it. And I have ported all the code from Mike Ash's page. I'm actually going to release this code as is. This isn't super long. I would really like to come back. And I would like to come back and try refactoring this to try to understand the pieces of it a bit more. I would like to, and then also I would like to create a particle simulation on top of this where I can drop in particles that sort of fly around based on the vector field. That is more like the reference on the GitHub thread. So I'm kind of imagining something like this, where I'm actually just going to draw particles moving around according to the vector field and see what that looks like. Then ultimately, I think what I want to do is try maybe moving to use one of these libraries, which has more a sophisticated solver and so this I think this project by Gabriel Weymouth I would like to take a look at. So I'll probably do some follow-up videos. I don't know if this was helpful or interesting. It was useful for me to try to do it. It took over an hour, but this is the process. I think, but if anything, this was useful to sort of see the process of trying to figure out somebody else's code written in another language and port it. We could try porting this to JavaScript and see if it performs even with just like raw 2D canvas. I'd be curious to see that. So go ahead and do that. Thank you to some comments from many people in the chat, but specifically Kay Weekman, who pointed out that I do not have turbulence if the viscosity is 0. So I now adjusted some things. So I created a viscosity of, and let me just zoom into this. I created a viscosity, a pretty low viscosity, but it's a non-zero viscosity. I also sort of changed the way I'm adding the density and removed that fade. And you can see this has more, even though this has more of the quality of turbulence. And yes, I challenge you now, take this code and add, it's filling up now, add rainbow colors. So what if you keep a separate RGB channel? So the things that I did, just you see is like, that I'm going to publish the code with this is I actually have a pretty low viscosity. Ooh, why did the time step get so big? The other thing that I also did is I adjusted the range of the angle to wrap around twice. So 2 pi times 2, because perlin noise is going to tend to give me values around 0.5, so it was really sticking around pi. So this now is my final version. Let me fix up some stuff here. If you are at the end of this video, hashtag Team Turbulence, okay? Hashtag Team Turbulence on Twitter. Let's blow it up. Of course, no one's going to have made it to the end of this video. But let's do this. Color mode, HSB 1. So my range is between 0 and 255. So let's do fill, D, 255, 255, 100. I think this is not what I want to do. Yeah, there we go. Except... There we go. Hue, saturation, brightness. That's pretty interesting. Team Turbulence all the way. This is my turbulence song. Team